Oops.
Okay, our next speaker in the ZAG Marathon is Pedro Montero, and his title is Geometry and Arithmetic of Equivariant Compactifications of the Affine Space.
Thank you for the invitation, and thanks to all the organizers and the Zoom hosters for making this possible. It's actually a really nice idea. I was really happy to be invited. So today I will speak about two joint works. A joint work with Jiyong Huang in Hanover, which happens to be here, and another one with Bahua Fu in Beijing, the Chinese Academy of Science. It's quite late for him. And both of them are quite related. About they treat about the geometry and arithmetic of equivariant compactifications of the affine space. So let me summarize very quickly what I'm going to talk about. So first of all, I will give a somehow historical motivation from both geometric and arithmetic point of view. Then I will start to speak about our results. I will give you the main ingredients that we used. And finally, I will sketch a particular case that I like very much. So that's more or less the plan for today. So everything started, I will say, with a problem by Hirzebruch in '54. Which is not exactly the same that I wrote here, but this version is more easy. So he asked for, you fix a dimension n, and he asked for classify all possible, well, at the very beginning, analytic compactifications of Cn, of the affine space. So you have some open set here, like, right, affine space. And you compactify this onto a smooth, say, projective or even compact variety, which turns out to be quite difficult if you don't impose any algebraicity assumption. So I will very soon, I will only consider projective variety. So everything will be algebraic. And that's the first thing. Then you can realize, I don't know, by Hartog theorem or by Krull theorem, that the boundary of this compactification, yes, so this guy, has to be a divisor, right? So you are looking for pairs, x and delta, where x is a smooth projective manifold, dimension n, which is fixed, and delta is your boundary divisor. And of course, if you are in dimension, say, at least 2, you can pick sub-varieties in your boundary, say points, and you can start to blow up them. So there's no unique, you can produce a lot of compactifications from, say, minimal one. So it's natural to impose some kind of minimality assumption, which is that the second Betti number of your variety is 1. So you can avoid this kind of blow-up thing. Well, a very first observation was made by Kodaira, and he observed that in this case, the variety itself, x, has to be a Fano-manifold, which I think has been defined several times during this conference. But here we go again. So we ask that the anticanonical divisor is ample, so you can use it to embed your variety into the projective space. Well, this is one thing, and the other thing is that the anticanonical divisor is actually a multiple of your boundary divisor. Okay, so these are two restrictions that you have in this situation. And in particular, since you are in a Fano manifold, you have that the second Betti number and the Picard number, the rank of the Picard group, right, are the same. So I usually will switch from one to another, and will even without noticing. So sorry about that. I hope it's clear, especially when I speak. So, of course, the first example is the projective space, right? You have a hyperplane at the infinity, and you remove this hyperplane H, which is Pn minus 1, and you get here an affine space. But what else? So, well, let's start by small dimensions. So in P1, you have, the only rational curve is, sorry, in dimension 1, the only rational curve is P1. And well, all curves have p curve number 1. So you need to impose some kind of restrictions. I mean, how to say, you're on P1, but how many points you can remove? You can check, I don't know, by looking at the fundamental group that you're allowed only to remove 1 point, in order to have something contractual. So you end up with only one possibility. Similar in dimension 2, you know after Kodaira and request classification, if you want, that the only minimal rational surface, the smooth rational surface, is P2. So again, you have a P2 and a boundary, and maybe it's a very nice exercise for first, I don't know, course in algebraic geometry, that if you're on Pn and you remove a divisor of degree D, hypersurface of degree D, then you end up with this group. This is the Picard group of the complement. So since your complement, you want that is the affine space, there's no possibility. You have to be, the boundary has to be linear. So in particular in P2, you have a line. Things start to get more complicated in high dimension, in dimension 3, and many authors working on this question for several years. So I'm very sorry I didn't wrote all the names here. Yeah, sorry about that. But it was finished by Furushima, the year 93. And the classification is as follows. First of all, you have the P3, the thing that I said before applies here, and you have a P3 with a plane. But new things appear. First of all, you have a smooth quadric, and you have this cone, this singular cone as a boundary. This is the cone over the projective cone over a conic on P2. This is here Q02 in this notation. And then you have also 4 more examples. You have B5 with a degree 5 Fano trifold of Picard number 1. I'm using the Skowski notation. I will come back to this. And you have another one of degree 22. And you have 2 possible boundaries, actually. These are surfaces, irreducible surfaces, but they can be actually very singular. For instance, one of these possibilities, I forgot, even allow non-normal boundaries. So yeah, it's not a very, how to say, nice compactification, but it's still a compactification of the affine space. Another thing that I should mention at this point also is that these are precisely the Fano manifolds of dimension 3 and Picard rank 1, which have an infinite automorphism group, which is a quite recent work, I think, of Yuri Prokhorov, Shramov, and Sasha Kuznetsov. So, well, these are kind of special Fano trifles. I will come back to this later. So, this is in dimension 3, and from dimension 4, I mean, higher, you don't have actually a complete classification, and first of all, of Fano manifolds, and nor classification of such compactifications. But there are some partial results and some nice compactifications by again, Yuri Prokhorov and Mikhail Seidenberg. So it's a very nice problem to find out the new compactifications of the affine space. But here we want to as I told you at the very beginning, I would like to have a more structure. I would like to have a group acting, and I will start to look at equivariant compactifications. So for today, I mean, maybe it's not this a very standard definition. I mean, but for today, a G variety where G is a connected linear algebraic group, will be a normal projective variety with an action, but I will assume that the stabilizer of a general point is trivial. This is one thing. And the second thing, that the orbit is dense and isomorphic to G as variety. So we have an action on G, we have on X, sorry. We have a dense open set, which as a variety is isomorphic to G. So we have an equivariant compactification of our algebraic group. So the first and very classical example of this is our toric varieties, right? That we have seen today as well. So we're very happy in this case because we have a lot of combinatorics, as we saw in, for instance, in Liana's talk. We can do pretty much a lot of things in a combinatorial way. But what I want to look at today are varieties which are equivariant compactifications of the vector group of the GAN. So we have the affine space seen as an algebraic group, unipotent commutative algebraic group, if you want. And you want to look at equivariant compactifications of this. And for shortness, I will say that these kind of varieties are additive, okay? And I will try to convince you that in this case, unfortunately, you don't have a lot of combinatorics, and you cannot hope of having combinatorics, but that's life. So let's see what happened. So that's from the geometric point of view and the geometric motivation. And there's another motivation to look at this kind of varieties that comes from arithmetic geometry. So there's a very classical result in arithmetic geometry that say that if you have a number field, so a finite extension of Q, and you fix a positive real number, then you can look at the points in the projective space over this field and look at the points that are of fixed height, how to say, bounded height. And it turns out that if you fix a height, a B, this set is finite. So let me just give a quick example. That was a theorem of Northcott. For example, if you're in the over Q, the field of rational numbers, then you have coordinates, homogeneous coordinates. You can, of course, clean up the denominators and suppose that your coordinates are integers. And then you can clean up, or you can also divide the greatest common divisor, and you can suppose that all your coordinates are relatively prime. And in that case, the height measures more or less the complexity of the coordinates. So it's defined to be the maximum of the absolute values. And then you can count, actually, and then you can convince yourself that this cardinal, is bounded by some constant, which is explicit, but I won't tell you what it is, times b to the power n plus 1. So this is a general problem in arithmetics that says the following. Once you have a variety over a number field with many rational points, I won't be very precise at this point, sorry. Then the Batire-Manning pair principle says that the asymptotic growth of this number MB should be controlled by the geometry of X. And again, I won't be very precise with what does it mean, but essentially it's, you can more or less forget about the number field and look at the geometry of, say, the complex number. And you have some geometric invariants, I don't know, lane bundles, degree, whatever. And it is a principle because as far as I know, at the very beginning was supposed to be a conjecture, but then some counterexamples were found. But even though it is very interesting to find out examples where this is true, and also more importantly, families where this is true. So in this on this line, a very first family of examples were, a very important family of examples was found by Batire and Chinkel in '98. And they prove that every toric variety is verifies this principle, this distribution of rational points are very well behaved in terms of distribution of rational points. And a very important result that motivated us to study these kind of things is a result by Chamberlois and Schinkel, very recent, that says that every additive variety is actually verifies this principle. So it is very interesting for also for an arithmetic geometry point of view to find new examples, to classify them, etc. So this is also a very nice motivation. So today I want to speak about the classification of additive Fano manifolds. Okay, so why Fano? Well, first of all, as I told you at the very beginning, if you are on Picard rank 1, second Betty number 1, this is automatic. By the remark of Kodaira, your variety will always be Fano. This is one reason. Another reason is that by result of Campana, Kolar, Miyaoka, and Mori, you have that the Fano varieties are rationally connected. So you can expect a lot of rational points. And the last thing is that by Kolar, Miyaoka, Mori, and very recently by Birkar, you have boundedness. So it is how to say, it's a well-stated problem to find out all possible additive Fano manifolds. You can actually hope for having a list if you fix the dimension and you are looking to a smooth varieties, right? Even epsilon log canonical if you want by Birkar result. So that's the goal for today. And let me tell you now how this story also started from geometric point of view. So I think the first result towards the more geometric understanding of this kind of varieties is a result by Hassett and Schinkel that says that for the projective space, there is a correspondence between the isomorphism classes of additive structures, namely how can you can put this GAN acting here, and local commutative artin algebras of dimension n+1. So this is a very nice correspondence. So you have a so you're how to say, you need only to understand the algebraic part. So let me give you an idea in dimension 2. So for P2, how to classify all possible additive structures. So you need to find commutative local artin algebras of dimension 3 as a C vector space. So you pick your ring of two variables, and you quotient by the following two ideals, right? This is the first ideal, second ideal. This is a very naive one, right? This is xy to square. And you can check that these two are not isomorphic. I don't know. For instance, you can check the Hilbert-Samuel series and check that they are different. And so you have two non-isomorphic algebras, nice algebras, like on the right side of the correspondence. And then you have a, well, this is a local algebra, commutative. You can take the exponential, which are nilpotent derivations, right? You take the exponential of elements in the maximal ideal. These are globally nilpotent derivations, not only locally nilpotent derivations. And you can projectivize your three-dimensional vector space, C3, and you get P2. So in that way, the exponential, since this is nilpotent, will be just a finite sum, right? It's not a series. And you can get a very explicit way to describe the action of J2 on the projective plane in this case. So in this example, the first one is the naive action. Is right, for example, so if you take x2 equals 1 here, you get the naive action of J2 on C2. And the second one is another action which is less naive, I would say, but it's obtained by considering this second algebra. And these are very different, actually. The first one have infinitely many orbits. Yeah, essentially the hyperplane x2 equals 0 is every point on this line is fixed. It's its own orbit, right? And the second one has 3 orbits. Well, this is a first thing that you have, and it tells you also that you cannot expect some kind of combinatoric like correspondence like in toric varieties, where you have a very nice correspondence between orbits and cones and so on. Well, here's not that easy, unfortunately. Not that nice. Also, even worst, if you call an the number of isomorphism classes of additive structures on Pn, then there is a class. Well, first of all, of course, I'm looking here at the right. You're essentially looking at the commuting matrices, right? Everything here on the right can be translated also in terms of matrices that commute. So this is a very, very classical problem, and actually was a problem that Supronenko looked at, and he classified these actions, these commuting matrices, sorry. And it turns out that in dimension 1, for P1, there is only one additive structure, the naive one. For P2, you only have these two. For P3, there are 4 different ways to compactify GA3 in an equivariant way. And well, here are the numbers. And for P6 higher, you have infinitely many ways to compactify GAN. So, well, that's life. But still, in say dimension 3, and low dimension actually, you can describe them in coordinates. It's not that difficult. And with this information, actually, Hassett and Schinkel, in this same article, they classified additive Fano manifolds of dimension 3 and Picard number 1, which are Fano by what I just told you about this Kodaira remark. They classify all additive ones, and it turns out that the only possibilities are P3 and the smooth quadric in P4. So let me go back a little bit. So among these 4 varieties, only the first 2 are equivariant compactifications, are additive. Right, and well, so the proof uses actually this classification. But so you have to rule out these possibilities. The last one is ruled out by using the following, which is also very interesting result. Proved also in the same article, that says that if x of any dimension and any Picard number is additive, smooth, then first of all, your boundary divisor is a union of this as many divisor as your Picard number is as your second Betty number. So you have like this, right? Here you have your AN. Here is delta 1, delta R. And well, this is a nice thing. And the second thing, which is more important actually, is that the anti-canonical divisor is a combination of these boundary divisors, but how to say, in contrast to the toric case, where you can put all the coefficients to be 1, here the coefficient has to be at least 2, and this is very particular to this group, to this algebraic group, and from this you can well just look at the equation and to this and realize that the log canonical divisor kx plus the boundary is not nef, right? Because it's well, due to the computation is more or less easy. So it's not nef. So this is very nice because it's very, from the minimal model program point of view, it's very convenient. Each time you have I mean, that's the whole point of the minimal model program. Have a log canonical divisor, which is not nef, and then try to run your MMP. So I will talk about that later. So the first result that we proved with Ji Yong was that concerns Fano threefold. So always smooth Fano threefold. So the case Betty2 equals 1 was is a result that I just mentioned by Hassett and Schinkel. So we treated the case of Betty2 greater or equal than 2. In that case, we have that every such additive Fano threefold can be realized as a, well, this is not a, how to say, this is just an easy way to say it. This is not a disjoint classification. I will tell you in a minute what that means. But any of these varieties can be obtained as an equivariant blow-up of P3, equivariant blow-up of the quadric, or a toric variety. What I mean that these three classes are not disjoint is that, of course, you can take, I don't know, the blow-up of P3 along, say, a line, and you get a toric variety. So these are not disjoint. Or the blow-up of the quadric at a point is the same as the blow-up of P3 at a conic. So, well, but this is just an easy way to state the theorem. A posteriori, after we have the list, we have that the Betti number is actually bounded by 4, the second Betti number, and that every additive Fano threefold that we studied, which is primitive in the sense that it's not the blow up along a curve of another one, of another Fano threefold, is toric. But this is just a, how to say, a posteriori analysis once you have the list, and you can only check the list and you can see this. But there's not more deep reason for that. It's actually a nice problem. I don't know how the answer, how to bound the second Betti number in a more uniform way. Say, well. And here, these are the varieties. If you know the list of Moria Mukai, you know they are listed by the Picard number, and then you have some numberings. So these are the Roman numbers stands for the Picard rank. So this is Picard rank 2, Picard rank 3, Picard rank 4. And the straight lines means blow up along a curve. So this, for instance, this variety is the blow up along a curve on the quadric. And these lines means the blow up along a point. So actually this variety is the blow up of the quadric on a point, which is isomorphic, I don't know, by taking a stereographical projection to the blow up of P3 along a conic. Well, these are the varieties, and well, then I mean, it's a natural problem to see if we can say something on high dimension, but there's no classification of Fano manifolds dimension 4 or higher. So we need to impose additional conditions. The very natural additional condition is to look at the Fano index of your variety. So if you have a Fano manifold, you know that the anticanonical divisor is ample. Also, you know that the Picard group of X is a lattice, right? It's set to the R, with R is the Picard rank. So you can ask yourself how divisible is your anticanonical divisor here in this lattice. Or in other words, you can ask whether this is the maximum integer such that the anticanonical divisor is a multiple of an ample divisor. Right? There is a classical result. I don't know, you can check by Riemann Roch if you want, that this number is belongs to 1, 2, 3, etc. till dimension of x plus 1. So these are all the possibilities. And the yoga is that if this index is high enough, then you can say more stuff. And actually, there is a complete classification of if the index is greater or equal than the dimension of x minus 2 by several authors. Again, I'm sorry, this is not very exhaustive list, but these are some of the, I will come back to this again in a few minutes. So this is a very nice, how to say, this is the, if you want to use the classification results, this is a very nice natural condition, is to look at the high index Fano manifolds. And that's what we did with Baohua-Fu, and we classified all possible Fano m-folds with high index. And well, there's a list, and for example, if you restrict yourself to the case of Picard rank 1, then you only find 11 families. And at the end of the talk, I will give you a very rough idea how to get one of these families. Well, and actually, we also have another result with Baohua, is that if you have a Fano manifold with Picard rank 1, well, by the result of Hassett and Schinkel that I just told you, the Fano index is at least 2, right? Because I just told you that the anticanonical divisor is a multiple of the boundary. In this case, the Picard rank is 1, so there's only one term here. And this coefficient has to be at least 2. So the index has to be at least 2. Actually, this is the way how Hassett and Schinkel, how to say, deduce that the Fano threefold B22 is not a equivariant compactification. So they only have to deal with the case of B5. And here we prove that under some geometric condition, actually the index has to be at least 3. So you look again at our theorem before, that stands for the index is at least dimension of x minus 2, then you can use it when the dimension of x is 5 or less. So this is a corollary. So if you have a Fano manifold of Picard rank 1 of dimension at most 5, and you assume that the BMRT, I will tell you in some minutes what this is, the variety of minimal rational tangents, the BMRT of x at a general point is smooth, then your variety is either the projective space, smooth quadric, or a linear section of the Grassmannian 2-5 of codimension 1 or 2. So this is also another way to recover the result of Hassett-Schinkel. Well, modulo checking this geometrical condition. But here you can recover in a more uniform way, if you want, the fact that the only threefold compactifications of the GA3 of Picard rank 1 are P3 and the quadric. And actually, there is a conjecture of Jung-Mook Huang that says that this condition should be always true for additive Fano manifolds with Picard rank 1. But as far as I know, it's still open. So this condition should be empty, but for the moment, it's not. And also, I will have to say, a priori this is not automatic. There are Fano manifolds for which the BMRT is singular. Whatever it is, this is not for free. There are results by Cinzia Casagrande and Stefan Druel showing that this may not happen. So let me give you some list of ingredients that we used. So of course, the very first, let me start with dimension 3. So the very first ingredient is the Skovsky and Mori-Mukai classification of Fano threefolds. So of Picard rank 1, we have 17. For Picard rank 2 or more, you have 87 plus 1, which is the Mori-Mukai classification. So you have 105 final trifles to check. Well, it's a finite list, but still very long, and some of them are not that easy. So you have to do it in a more clever way. And the way to do it, at least the very first thing that simplifies a lot of life, is the so-called Blanchard's lemma, which was stated in the very beginning by Blanchard in an analytic setting, and it was reformulated or generalized to the more algebraic setting by Michel Brion. So let's call it Blanchard-Brion lemma. And I won't state what it says precisely. I will just tell you what we used about this lemma. So we used that two consequences. The first of all is that if you have a blow up, say between two smooth predicted varieties, if X is additive, then Y has to be additive as well. So if the source is additive, then the target, it is also additive. And the second one is that the automorphism group of the product, the connected component of the identity, is just the product of the connected components of the identity. So in practice, for instance, if you have a blow up, if you're looking at one of these 105 varieties, and you manage to see that your variety is a blow up of a Fano variety, Fano threefold of Picard rank 1, which is not additive, in other words, which is not P3 nor the quadric, then for free, you have that X cannot be additive. So this simplifies a lot the things. A second thing is that if you, by a result by Mori and Mukai, if your Picard rank is 6 or higher, then your Fano threefold has to be a product of a Del Pezzo surface and P1. And actually the degree of your Del Pezzo surface, since the Picard rank is high enough, the degree of the Del Pezzo surface has to be low. And in particular, low enough such that the automorphism group of this Del Pezzo surface is actually finite. So if you look at the connected component of the identity, it's just trivial. And then you end up with the connected component of the automorphism group of this guy is just PGL2. And of course, this is a three-dimensional, non-commutative algebraic group, so you cannot fit inside GA3. Well, then you can start to look at some special varieties. So the first kind of course, a very nice Fano variety are toric varieties. So there is a classification of polytopes, fans that we also saw this morning with during Liana's talk. So there is a very nice and explicit description of all possible smooth toric Fano threefolds. You have 18 of them. And there is a quite recent result by Ivan Arjantsev and Romanskevich that says that how to characterize additive toric varieties in terms of their polytopes. So, for instance, you have here such a toric Fano threefold. There is some condition that I won't tell you, but you believe me. I mean, our toric varieties, you expect that you have some combinatoric way to understand things, and there is. And you can check by hand actually that among these 18 toric threefolds, only 14 of them are additive. And of course, once you know the answer, you can start also to clean up the arguments and see more geometrically that some of them are actually additive for other reasons. But that's pretty much the idea for toric varieties. Then you can ask for flag varieties, homogeneous varieties if you want. For instance, a very nice example is the predictivization of the tangent bundle of P2, right? This variety. So this is a Fano threefold, and you cannot, I mean, this has this is not a blow up of another finite treefold. It's primitive, if you want. So you cannot use the Blanchard lemma's argument. You have to do something else. And we use the fact that this is a homogeneous Fano variety. And there is a nice result by Ivan Arjantsev again, which tells you how to recognize additive Fano varieties among these homogeneous varieties. You have to look at the unipotent radical, and it has to be of this parabolic group, and it has to be commutative. Or this pair has to be exceptional. And for instance, in that way, you can check by hand, by looking at matrices, that your variety is not additive. Then you have, again, by Sharoyko, Arjantsev, Popovsky, you can have also explicit description on quadrics. So you can do it kind of the same thing in coordinates, the same thing that you did for the projective space, P3. Alhazen Schinkel, you can do it for quadrics. And the very last but very important result that we used is that Takashi Kishimoto classified all possible compactifications of the affine space, actually not only the affine but also contractible, but in particular affine space, that compactify into Fano treefolds of Picard rank 2, and under an additional condition, which is that the log canonical divisor is not Neff, which happens to be our case because of the Hasetan-Schinkel result that I just told you. So Kishimoto found 16 possible X, and even more, he found also the possible boundaries. But among the 16 possible X, we can check that only 6 of them are additive. And that was actually the starting point. Then you can start to look at, I know, somehow the family tree that I showed you before. And then you can try to do some arguments and, well, cover all the classification by Skovsky and Morimukai, pretty much. So let me finish with the high dimensional case very quickly. So as I told you, in this case, you have to look at the Fano index. So, and when the Fano index is higher, or when the co-index is lower, then you can say more. For instance, if the index is maximal, then you are exactly in the projective space case. These are resolved by Kobayashi Oshiai. Similarly, on co-index 1, you are on the case of a quadric, again by Kobayashi Oshiai. There is a complete classification in the case of co-index 2 by Fujita, and complete classification of co-index 3 by Mukai, Mella, and Wisniewski. So you have also lists, and here you divided your analysis into 2 cases. The first case is more or less similar as what we did before, higher Picard rank, and you can use, say, the equivariant MMP using this Blanchard's lemma. I won't say anything about it. And the second case, which is the minimal case, is the Picard rank equals 1. And here there is a tool that you usually use for this kind of Fano manifold, which is the BMRT, studied by several authors and mainly by Jung Huang, Mok, Kievekus. So I won't define what exactly it is, but the idea is very geometric. So you have a Fano manifold of Picard rank 1. You know that this is uniruled. So for a general point, you have a lot of rational curves. Since it's a Fano manifold, you have a natural way to compute the degree of a curve by computing the intersection with the anti-canonical divisor. So you look at the minimal rational tangent, say, and so the rational curves of minimal degree, and then at the general point, you look at the tangent directions. So this fill up a subvariety. I mean, you take the closure if needed, and you fill up a subvariety of the projectivization of the tangent bundle. And this is the VMRT in a drawing. And you ask, I mean, this is a tool for studying Fano variety of Picard rank 1. And the condition that we ask, the condition star that I told you before, is that this guy has to be smooth. This red thing has to be smooth. So let me very, very briefly tell you how to give the following result. How to obtain the following result. Given a Fano manifold of Picard rank 1, which is a Del Pezzo manifold, so the index is dimension of x minus 1, I will show that x has to be a linear section of the Grassmannian 2-5 of codimension at most 2. Okay, so that's the plan for this last 5 minutes. So first of all, you have the Fujita's classification. You know all the possibilities for x. And the first, well, here they are, a cubic intersection of two quadrics, a quartic on a weighted projective space, a sextic on a weighted projective space, and our linear sections that we are looking for. So the first three possibilities are not that difficult because you can actually compute that the automorphism group is finite. So you cannot embed a vector group inside. The first possibility is more subtle. In this case, you obtain a variety of Picard rank 1. You look at the generator of the Picard group. This is an ample divisor. And I mean, this is very explicit, right? You have equations and you can compute actually what are the global section of this guy. And you can compute, because you are on a weighted projective space, you can compute the map and you can check that this is not birational. And by a result of Huang and Fu, you can actually check that this is not possible. It has to be birational. So you can rule out this possibility and you can, so we need to understand what are the possible, first of all, yeah, what are the possible linear sections that are of the Grassmannian 2-5, which are additive. Okay, so that's the goal. So first of all, if X is an additive Fano variety with Picard rank 1, then the condition star that I just told you that this BMRT is smooth implies that this BMRT that may have several components, right, is actually irreducible and linearly non-degenerate. That what means that the linear span of this variety is the whole projective space. In particular, since it's linearly non-degenerate and irreducible, cannot be a point, right? So it has dimension at least 1. This is important. And secondly, we can check by general things about rational curves on algebraic varieties, right? That the Fano index, in this case, actually can be computed as the intersection number of the anticanonical divisor and one of these minimal rational curves. This is exactly our index. And by deformation theory, also again by the general theory of rational curves on algebraic varieties, you can compute that this number, this index, is actually the dimension of the VMRT plus 2. And since we know that this dimension is at least 1, then the Fano index is at least 3. That's what I just told you before. And you have to check then that this condition actually holds for linear section of the Grassmannian. This is not that difficult because there are a lot of people that worked on homogeneous VMRT of homogeneous varieties and their linear sections. So you can check it actually, and then you can apply this, and you have that the index has to be at least 3 by this by the third point. But the index is n-2 because you are in the Del Pezzo case. So it has to be of dimension at least 4. Or in other words, the codimension of X inside the Grassmannian is 0. I mean, it means the Grassmannian itself, or codimension 1 or codimension 2 section. And here again, something funny, you cannot have codimension 3 linear section, which is actually V5 that I told you at the very beginning of the talk. This is nice because, well, this shows you also that the way that the group action cuts by hyperplanes can be weird. And And finally, you can check that actually the Grassmannian 2-5, which is a homogeneous Fano manifold, is additive thanks to this Argentsev criterion using this unipotent radical. And then you can also check that the linear sections are actually additive by a result of Huang and Fu. And I think that's pretty much it. Thank you very much.
Okay, thank you, Pedro. Let's applaud audio or digitally. Are there any questions? Feel free to turn on your microphone if you want to ask. Okay, so Pedro, maybe I'll ask one.
Yeah, sure.
Yeah, so I got lost at the end about which cases in Mori-Mukai, which Picard rank cases you've established the result. It's all of them? You found them all now?
Yeah, all of them. Yeah. I just show you this case for, I mean, because I like this case.
You specialize to see a method of proof, and then
actually sorry. Actually have all of them. And for example, for fourfolds, if you believe in this star condition is okay, the only case that remains is the Fano fourfolds of Picard rank at least 2 and Fano index 1.
Okay. So as someone who has studied mirror symmetry for many years, I have to ask the following question. What is the mirror analog on the Landau-Ginzburg mirror to these phanos of the additive condition on the Fano?
Oh.
I'm not saying you know the answer, you probably shouldn't, but I think it's an interesting question. You cut down to this beautiful subclass, it's a natural subclass. What does it mean on the Landau-Ginzburg mirror side?
Actually, I don't know the answer.
Yeah, so I'd be happy to communicate with you by email about that after the fact if you're interested. After the talk.
Yeah.
Okay. All right. Any other questions for Pedro? Okay. If not, let's thank him one last time.
Thank you.